Hello and welcome to A level chemistry online. This video is a part of Unit 1, Atoms Bonding. More specifically, this is the 5th video of Atoms and Bonding. It is about the electron configuration of atoms. In this video, we are going to look at a quantum mechanical model of the atom. At the end of this lesson, you will be able to 1. Describe a model of the atom using quantum numbers. You'll be able to write the electron configurations of the first 36 elements in the periodic table. And 3, you will see why the periodic table is organized into blocks. So far, we've talked about the nucleus of atoms, about mass and about charge, but we have talked very little about electrons, except to say that they are found in clouds. Here's a picture of a cloud around the nucleus. So this is a very vague term. In this video, we are going to shed a little more light about the nature of these clouds. This is chemistry, and we can't go any further without discussing electrons. It is the behavior of electrons which give the elements their chemical properties, and we will soon see how this is linked to the periodic table. The person attributed with the modern organization of the periodic table was a Russian chemist named Dmitry Mendeleev. He spent years grouping elements according to their chemical properties. Those of you who have studied GCSE in chemistry may know Mendeleev assumed that the list of elements was incomplete at the time of his work, so he left gaps which were later filled with elements as they were discovered. Little did he realize at the time that the table he was constructing would become a template for the quantum mechanical atomic model. In a simple form, this model will be explained here. As we increase atomic numbers in a list of elements from 1 onwards, for each new element, as the atomic number increases by 1, the numbers of protons and electrons in the atom also increases by 1. However, it's apparent that if you group elements according to their properties, that this list should not be a simple sequential order of the elements. For example, helium is more like neon than it is to just about anything else in the periodic table. Similarly, sodium and potassium have very, very similar chemical properties. And the chemistry of chlorine is more like that fluorine and bromine than it is to many other things. A group of spectroscopists, amongst them Niels Bohr in the early 20th century, was studying the emission spectra of atoms, and they noticed that emissions from atoms were clearly defined by very specific energy levels. They needed an atomic model that could account for these observations. It was the spectroscopists and theoretical physicists that started to build quantum mechanical models of the atom. An electron within an atom can be described with 4 quantum numbers. The principal quantum number, designated n, can take whole number values. So n can equal 1, 2, 3, etc. This describes the shell or the main energy level that an electron exists in. The angular momentum quantum number, L, can take values from 0 to n minus 1. Where n equals 1, the only value for L possible is 0. This gives rise to a spherical orbital. So this is a volume, a sphere, and it's denoted an s orbital from spectroscopist language, meaning sharp, for a sharp peak in the spectrum. When n equals 2, the values of L can be equal to 0, and n minus 2 minus 1 is 1. This gives rise to one s orbital and a set of p orbitals. So these orbitals themselves represent probability functions of finding the electron that they're describing in that location. So an s orbital is spherical, a p orbital is a kind of dumbbell shape. When n equals 3, L can equal 0, 1, or 2. So this would give rise to one s orbital, a set of p orbitals, and a set of d orbitals, which are kind of this, like, say, cloverleaf shape, with an extra lobe on it. That's d orbitals. So again, these are like three-dimensional structures. When n equals 4, L can equal 0, 1, 2, 4. 4 minus 1 is 3, which gives rise to S, P, D, and then it gets a very complicated, and an F. So it's an S, P, D, and F orbitals. So in spectroscopist language, this is sharp, pronounced, diffuse, and faint. That's how I always remember it. Magnetic quantum numbers denoted L sub M subscript L can take values of plus L to minus L. So to minus L. So if L equals 0, ML equals 0. L equals 1, ML equals minus 1, 0, plus 1. If L equals 2, ML can equal minus 2, minus 1, 0, plus 1, and plus 2. And if L equals ML can equal minus 3, minus 2, minus 1, 0, plus 1, plus 2, and plus 3. So this gives rise to the number of each kind of orbitals. So we get to these are s orbitals, we could just get 1 because the value one value of 0. For p orbitals, there's 1, 2, 3 values. There's three orbitals to a p orbital. If L equals 2, then we can have 5 d orbitals, and if L equals 3, we can have 7 f orbitals. So 1 s orbital, 3 p orbitals, 5 d orbitals, 7 f orbitals. Finally, we have the spin quantum number, denoted ms. So for each orbital, an electron can occupy it with either spin plus half or spin minus half. Each orbital can hold up to 2 electrons with opposing spins. So a plus and a minus have to go together. You can't have 2 plus halves. Each electron in an atom has its own set of quantum numbers. So, how do we apply this knowledge to electronic configurations of atoms? Well, we can put all of this into a table. So let's start. Here, on this column here, very important column this, we're going to have energy. This is low energy and high energy. So low energy is nearer to the nucleus, high energy is further away, much further away from the nucleus. The shell, noted by N. The subshell, denoted by L. ML, number of orbitals. MS. So if I take the number of orbitals and times it by 2, gives me the maximum number of electrons for each orbital and for the subshell. The subshell. And here, maximum number of electrons per shell. So let's fill in the first one. This is the first shell. So if we remember the first shell, we have one subshell. The orbital is an s orbital, and we have one of these, and we can have 2 electrons in this, and a total of 2 electrons in the shell itself. Let's make that line across here, and let's fill this, draw these divisions. 1, 2, 3. 1, 2, 3, and then finally a fourth. So this represents the second shell, the third shell, fourth shell. We have S, so S and P orbitals, S, P, and D orbitals here, and S, P, D orbitals here. So again, for all the S orbitals, we can have 1 orbital. So let's fill those in. For the P orbitals, we can have 3. Remember, 3. For the D orbitals, we can have 5. And for the F orbitals, we can have 7. So therefore, the maximum number of electrons that we can have in each subshell is going to be 2 plus 2 plus 2 plus 2. So 2 here and a 6 here, 2 here, 6, 10, 2, 6, 10, 14. So therefore maximum number of electrons per for the shell then becomes 8, 18, and 2 plus that's 24, 30, 32, 32. So this isn't the same as the Bohr model that some of you might have learnt during GCSE. There are actually quite differences in the total numbers of electrons that can exist in the different shells. So there are just 2 more points that I'd like to make. One of them is, if I draw a little line here and basically expand that out to here and here. In terms of energy, the 3D and 4S are very, very close together. Indeed, what we see in reality is that in actual fact, 3D orbital is slightly higher than the 4S orbital in energy. So these actually flip over when we come to draw out electronic configurations. And the final point is that for the sake of the A-level exam, we actually cut off the chart at this point. So if we completely fill up, count the electrons up to this point here, this brings us to 36, which means that the atomic number is 36. And down here, we don't need to know it. So just a quick mention of 2 rules that we use when we're filling out electronic configurations. One is the Aufbau principle, and the second one is Hund's rule. So if we imagine that I've got a long thin beaker here, this is a measuring cylinder maybe, so look here, we have our 1s orbital, 2s, 2p, 3s, 3p orbitals, and I've got a cup. And I'm pouring the contents of this cup into here. And this cup is full of unpaired electrons. And there's 15 of them here. So we're talking about a phosphorus atom. So this is an example, 15 electrons. That's phosphorus in the periodic table. The Aufbau principle, so at the bottom of the cup, these are lower energy and these are higher energy. So let's just say energy low and high. So if I'm pouring these in, I'm going to fill up the electronic configuration of phosphorus from the bottom to the top. Five, 6, 7. Notice how I'm doing this here. And I'll talk about that in a second. 8, 9, 10. So that's 8, 10, 11, 12. And then to fill in the last 3, I'm going to use something called Hund's rule, which is that adding electrons to equivalent orbitals, when adding electrons to equivalent orbitals, I fill them up so that electrons go into an unoccupied orbital with a parallel spin first before pairing them up with opposing spins. So the next 3 electrons go into here with parallel spins. This is the electronic configuration of phosphorus, which I could write now 1s2, 2s2, 2p6, that's got 6 electrons in, 3s2, 3p3, because the 3p's got 3 electrons in. So for the first 36 elements, let's start writing out the ground state electronic configurations of their atoms. Remember, this is an important note. These are atomic materials not involved in compounds. So you can have a element, and then here ground state. So that's ground state is the lowest energy state. Electron configuration. So we start off, H1 is going to be 1s, 1 electron. It's got 1 electron on it. It's going into the lowest energy level, which is the 1s orbital, and it's got 1 electron in it. He2, 1s, got 2 electrons in. And the next one is lithium, 1s2, 2s1. Beryllium, 1s2, 2s2. Boron, 1s2, 2s2, 2p1. And I can go on and on and on and on. Let's put in another example. Let's say iron, 26. And I'll put this in 1s2, 2s2, 2p6, 3s2, 3p6. After because the 3d and 4s are inverted, the next one is the 4s, 2, and 3d, 6. So 2, 4, 10, 12, 18, 20, 26. So that's the right electronic configuration for iron, an iron atom in its ground state. That's elemental iron. If I was to make it into an Fe2 plus ion, then I would simply knock off 2 electrons here, or even take these 2 off and leave that as a 6. So for the 2 plus, we could write it out as so up to here. This is the electronic configuration of argon. So I could write argon here and then just 4s2, 3d, 4. And this continues on all the way down to krypton, which is number 36. And the electronic configuration is 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, 3d2, 3d10, 4p6, and that should now equal 36. So if I add all those up, it's 16, 18, 24, 26, 32, 34, 36. So that gives us 36 electrons. So that's the electronic configuration of krypton. If we're a little bit worried about this 4s orbital coming before the 3d orbital, so maybe we'll forget this in an exam context, there's a very good reminder that's available for you if you just choose to look at your periodic tables. So here, so in the periodic table, going down, these are called groups, and then going across, these are called periods. So first period, this is the second period, this is the third period, and at the bottom here is the fourth, third period. So this first period is the 1s orbital being filled. This is the 2s orbital being filled, and the 2p orbitals being filled, and then finally the 4s, and this is the first set of d orbitals, which is the 3d orbitals. So it's actually in the order, and we fill them up in the order that they're shown in the periodic table. Now remember, at the beginning I was telling you about Dmitry Mendeleev and how he grouped the elements according to their chemical properties, and how this turned out to be a template for the quantum mechanical model of the atom. The chemical properties of the elements are determined almost entirely by the outermost configuration, that is the highest energy configuration of their electrons. We will look at this further in units 3 and 4. When this video is finished, I would like you to take a look at exercise 1.4. So to recap, in this video we've described a model of the atom using quantum numbers. We've learned how to write the electronic configurations of the first 36 elements in the periodic table. And hopefully you would have seen why the periodic table is organized into blocks. If you haven't, then completing exercise 1.4 will help in that. So that I expect that you'll have to go through this video several times, and possibly to take a bit at a time. It's quite heavy going for the uninitiated. Please take the time and the care to learn this as best you can. Because the model presented is relatively simple, but the implications and the power to explain are very, very far-reaching. Thank you for listening.